Hello students, welcome back to our Chapter 3 Chemistry 1510 video notes. Today we're going to wrap up Chapter 3 by talking about empirical and molecular formulas. So you already know what a molecular formula is. It's the formula of a molecule. So an example of that might be something like, how about sugar? Right? So sugar has a formula of C6H12O6. So this set of atoms, when they are bound together, they actually make a molecule. And the problem is, when we go through the math that we're going to do at the second half of this video, is that when we do the math gets us the smallest whole number ratio for something like sugar. So notice how 6 can go into 12. So our smallest whole number ratio for this would be CH2O, because we can divide each of the subscripts here by 6. Let's look at another example. When you were learning how to name things, one of the things that you named was P4O10, which is tetraphosphorus dicoxide. And so if you look at P4O10, notice how here the 4 and the 10 have something in common. They're both divisible by 2. And so we can write the empirical formula, as P2O5. So let's look at how the empirical formula and the molecular formula are related. What I mean by that is, if I gave you an empirical formula and a molar mass, how would you calculate the molecular formula? Right? So what I'm giving you, if we look at an example, if we look at this example, we're searching for the C6H12O6. We don't know what that is the answer to the question. So I'm going to give you the molar mass of 180.15 grams per mole, and I'm going to give you the empirical formula. And that's CH2O. And the question is, how do you use this information to get this answer? So what you're going to do is a quick division. You're going to figure out the mass of the empirical formula. And you're going to then figure out how many times this empirical formula mass can go into the molar mass. So if you calculate 12, right, for carbon, 2 for hydrogen, 16 for oxygen, that's about 30. So we're going to have the mass of the molecular formula. We're going to divide that by the mass of the empirical formula. And when we do that, we're going to not freak out that we have some decimals here. We're going to get really close when we do this division to about 6. So that's my about sign. So what that means is then we can take this 6 and we can distribute that 6 through to the coefficients, the subscripts at the bottom of the empirical formula to get our molecular formula. So C1 times 6 is C6, H2 times 6 is H12, O1 times 6 is O6, and so we ended up with the molecular formula. So we're starting with this because this is the simpler part of the process. It is much easier to go from the empirical formula to the molecular formula than it is to find the empirical formula in the first place. So I'm going to give you some space to try to figure out what the molecular formula for hydrazine is. So you should be able to maybe pause for a moment, go through the same process, mimic that, and then hydrazine is N2H4. So if you get that, you'll know that you have that process down pat. In the meantime, let's go ahead and try some problems where we just figure out the empirical formula, and then we can connect the two ideas a little bit later. So in this question, this is a super typical empirical formula question. In this empirical formula question, it gives you the mass of a sample, and it tells you how much of one component you have, nitrogen, and that the rest is oxygen. So it doesn't tell you the mass of the oxygen. That's something that you need to figure out. But if you know that the mass of the sample is given, then you can take the mass of the sample and subtract out the mass of the nitrogen. And the reason that this works is because you only have two components, right? You only have oxygen and nitrogen in your sample. So if you know the total and you know the nitrogen, you can find the oxygen, which is what we did. So that's a great place to start. Then what we want to do is our ultimate goal is to find out what the coefficients are in our N, X, O, Y kind of formula here. And remember that those coefficients need to be whole numbers. And also remember that we said that if we had like 1 mole of H2O, it contained 2 moles of hydrogen and 1 mole of oxygen. So these numbers here, the X and the Y, need to be mole ratios. So we are given a mass to start with. So we're given the mass of nitrogen. We need to get to moles of nitrogen because we need a mole ratio. So think about how to change your grams of nitrogen and your grams of oxygen to moles. And remember, our nitrogen and oxygen here are not diatomic because they're in a compound, right? Once they're in the compound, they are no longer diatomic. So when we do this math, we are going to convert our oxygen and our nitrogen to moles using our regular old molar mass, not doubling it. So we're going to calculate this, do this division, and here's the thing. These numbers that you get are going to be really small. And if you want, you can kind of maybe forego limiting yourself with your significant figures, right? I would do at least 4. But the work that I did when I kind of pre-prepped these problems, I actually did everything my calculator gave me, which was 5 digits. And that just makes the division nicer later on. So notice how we also said that the numbers of X and Y needed to be whole numbers. And here what we have is definitely not whole numbers. So we need to find a way to make those whole. And so one of the things that I think is, I guess, the easiest route to do is to pick one and divide each of the values by the number you've chosen, and you should choose the smaller of the two. So here, the 799 is smaller than this one that has an 8 right here. So we're going to divide both of these by that smaller value. And that is going to get us for sure 1 whole number here, right? So it's telling you that you have 1 mole of nitrogen. And then you compared your moles of oxygen to your moles of nitrogen. And so this is going to be pretty darn close to 1. So that means that our X and our Y are both 1s, but remember in our chemical formulas, we don't write in those ones. So I'm just going to sneak back in and erase those. And I'm going to scooch that oxygen a little bit closer so it looks better. And so your answer here is, your empirical formula is NO. So, which is nitrogen monoxide. When we look at the molecular formula, we don't have enough information in this problem to take that empirical formula and convert it to a molecular formula. We'll worry about that a little bit later. What I want to do is show another setup, another way a problem could be given to you. So in this first problem up here, they gave you the masses of the sample and the nitrogen. In this problem here, what you're seeing is you're given the percentages. So you're given the mass percents. And we can use mass percents too. There's just one thing that you need to do first. You need to assume a 100-gram sample. The reason we assume a 100-gram sample is because with this assumption, your percentage, you just replace it with a gram, because 1 percentage point equals 1 gram if we assume a 100-gram sample, which sounds great. So, oops, that's not what I wanted to do. I just wanted to give myself a little more space. Okay, so then we're going to start the same way. We are going to take the 69.58% barium, and because we're assuming a 100-gram sample, we're going to take the percent, we're going to put a gram in its place. We're going to go through the same process by calculating the number of moles of barium. And so we're going to do the same thing for carbon. We're going to take your 6.090%, put a gram where the percentage is, because we're assuming a 100-gram sample. So in your 100-gram sample, 1 percentage point is going to be equivalent to 1 gram. And then we'll divide by the molar mass of carbon to get our moles of carbon. And then we're going to get to oxygen, and we're going to take our 24.32% oxygen. We're going to put a G in because 1 gram equals 1%. And then we're going to turn our grams of oxygen into moles of oxygen. All right, remember, we're writing down at least 4 sig figs for all of these because it's going to make your division nicer. So we have about a half a mole of barium, about a half a mole of carbon. Oops, 1 decimal place too far. Let's fix that. That's better. And then 1.520 moles of oxygen. So we're going to do the same thing that we did before. We're going to pick the lowest of these 3 numbers that we've calculated, right? So we're picking the lowest out of these 3. Now, in this particular case, barium and carbon have the same amount of moles, so it doesn't really matter which one you choose, right? It's the same numerical value. You're going to do that division. Now, the reason that we're dividing by the smallest number is because then we are for sure getting at least 1 whole number. And in this case, we're getting 2 whole numbers. Now, if you put the 2.520 moles divided by the 0.5070 moles in your calculator, right? If you'd put that in your calculator, what you end up with is 2.99. And we need whole numbers. But thankfully, 2.99 is super close to 3. So we are very happy to call this barium carbonate. And notice how in some cases your empirical formula that we have here is the same as a molecular formula. Because barium carbonate's an ionic compound, this is the chemical formula for barium carbonate. So I have one more question here, and let's see what to do. Ooh, this one's a good one. Oh, wow. I'm so excited. So for this question, this one is definitely harder than the other questions because this one is combining a combustion analysis with an empirical formula. So let's talk about how I knew that. See how it says you have a hydrocarbon that undergoes complete combustion, and then it gives you carbon dioxide and it gives you water. So in this case, you have to start your empirical formula problem differently. You have to go back to the knowledge from the combustion section and work on it from that direction. So what I mean by that is, remember your hydrocarbon, you didn't know the chemical formula, but you knew it burned in oxygen, and you also knew that all of the carbon turned into the carbon and carbon dioxide, and all of the hydrogen turned into the hydrogen in water. And so what we need to do is start with these two numbers and do the same thing that we worked on just now, getting to moles of carbon and moles of hydrogen. It's just going to start from a different place. So for this one, we're going to start with our grams of carbon dioxide and our grams of water. Remember that our molar mass of water is about 18.02 grams of water and 1 mole of water. And we want to take this all the way to moles of just hydrogen. Because remember, we said momentarily, just a couple of moments ago, that when we are searching for the X and the Y, what we need are mole ratios and whole numbers. So right now we have grams of water. We want moles of hydrogen. So we're in moles of H2O, and now we can take our moles of H2O and say for every 1 mole of H2O, we have 2 moles of hydrogen. Okay, let's do the same thing with CO2. CO2 has a mass of 44.01 grams of carbon dioxide in 1 mole of carbon dioxide. So then the same thing here, we don't want grams of carbon dioxide. We don't even want moles of carbon dioxide. We want moles of carbon. So we have one more term to put in. 1 mole of CO2 contains 1 mole of carbon. So at this point, we should stop and ask ourselves, do we have the information we need? So we have things in moles, so that's good. There's no reason to continue and do grams here, right? Because that's what we did in the past. We said 1 mole has 1.01 grams, but that's not necessary here because we want to be in a mole ratio. So what we'll do is we'll stop at this point and we'll calculate the number of moles of carbon and the number of moles of hydrogen. And at this point, I want you to try and finish this on your own. See if once you've gotten to here, if you can mimic that empirical formula process. And what we can do is double check that you can when we see each other in class. So that's going to be all. I'm going to let you try that one on your own. You got some good examples above to work with. So I will see you soon. Thank you for your attention. And this is Katoni signing out.